Hello, my name is Kevin Craig. This presentation is on dynamic system response, and I focus on the essential elements of dynamic system response. You have extensive notes on this topic, and I've extracted the key elements that you need to have at your fingertips each and every day as you solve engineering problems. Here we see a mechatronics system design team made up of a mechanical engineer, an electrical electronics engineer, a controls engineer, a computer systems engineer. They all work together in an integrated fashion to come up with a mechatronic solution to the problem at hand. And here is our mechatronics diagram that shows the essence of this field that has come to be known as mechatronics. Linear time invariant systems, or LTI systems. A frequency domain transfer function is limited to describing elements that are linear and time invariant. These are severe restrictions. No real-world system meets them. Linear time invariant system properties are the following. Homogeneity. If you have an input R and an output C, then if you multiply the input by K, the output will get multiplied by K. Superposition. If the input R1 leads to an output C1, and input R2 leads to an output C2, then if you combine the inputs, the output will be the sum of the individual outputs. That's superposition. Lastly, time invariance. If you apply an input at time t, you get a response, C, at time t. If you delay the input by a time t1, then the output will get delayed by a time t1. That's called time invariance. Transfer functions, the basis of classical control theory, require LTI systems, but no real-world system is completely LTI. There are regions of nonlinear operation and often significant parameter variation. Examples of linear behavior include addition, subtraction, scaling by a fixed constant, integration, differentiation, time delay, and sampling. No practical control system is completely linear, and most vary over time. LTI systems can be represented completely in the frequency domain. Non-LTI systems can have frequency response plots. However, these plots change depending on system operating conditions. Here's a diagram showing how physical model hardware parameters are related to physical model dynamic system performance. Let me take you through this diagram. Everything starts with an actual engineering physical system. This is a system we want to understand, we want to improve. We use engineering judgment and simplifying assumptions to come up with a physical model, a model that captures the essential attributes of our real physical system. We call the first model we developed the design model. It's simple, but again, it captures the essential attributes of this physical system. To the physical model, we apply the laws of nature. The result of that is a mathematical model, a mathematical representation of the physical model. The mathematical model will have hardware parameters in it, and these parameter values need to be determined either by experiment, calculation, consulting reference documents, and so forth. The mathematical model will be zero order, first order, or second order ordinary differential equations. Higher order models may result, but usually they can be represented by combinations of zero, first, and second order dynamic system models. Once we have our mathematical model with hardware parameters, we then take the step to put these differential equations with these hardware parameters into standard form. The standard form The zero order, first order, second order dynamic system models have a standard form. The parameters in the standard forms include steady state gain, time constant, damping ratio, natural frequency. We use these standard form models, mathematical models, to predict dynamic performance. We can relate these parameters to dynamic performance. What dynamic performance? Dynamic performance is concerned with speed of response, relative stability, meaning if the system is stable, how close is it to being unstable? These are stability margins, and steady state error. So I can relate these performance indicators to these parameters in the standard form, and I can relate the parameters in the standard form to the hardware parameters. So if performance is not acceptable, determine what the standard form model parameters should be to give you acceptable performance. Then modify the hardware parameters to achieve the desired standard form model parameters. Then verify predicted dynamic response by simulation and also by experimentation if possible. This process is very, very important to understand, and it's the reason why we use the standard form, because to relate the mathematical model with hardware parameters directly to performance requires simulations, maybe tens, hundreds, thousands of numerical simulations to get any kind of an insight, to know in what combination you need to change the hardware parameters to get a certain performance. So this is very important. Let's review the electrical mechanical analogy. Force is analogous to voltage, velocity to current, the damper to a resistor, the spring to a capacitor. Note that K is analogous to 1 over C, the mass to an inductor. The constitutive equations for a resistor are Ohm's law. E is equal to IR. For an inductor, voltage across the inductor is proportional to time rate of change of the current through the inductor. For the capacitor, voltage across the capacitor is proportional to the integral of the current through the capacitor with respect to time. The resistor is the same as the damper. Force is proportional to velocity. The coefficient of proportionality is the damping coefficient B. For the mass, force equals the mass times the time rate of change of the absolute velocity, which is acceleration. And for the spring, we know F is equal to K times X. F is equal to K times the integral of the velocity with respect to time, which is X. What is a zero-order dynamic system model? Well, the output is proportional to the input. It's instantaneous, it's perfect. Here is the equation that describes it. It's algebraic. Q is the output, Q0, QO is the output, QI is the input, K is the constant. So the output is proportional to the input. That's the block diagram. This is the operational transfer function or the Laplace transfer function. The output over the input is just a constant. This is the sinusoidal transfer function. This just tells you the amplitude ratio is K, and the phase angle between the input and output sine waves is 0 degrees. So if I input a step into a zero-order model, I get an instantaneous response that's proportional to the magnitude of the step. For frequency response, if you input a sine wave into a linear system and you wait for the transients to die away, in the steady state, the output will be a sine wave. Same frequency, has to be. The amplitude will be a function of frequency, and there'll be a phase shift that's a function of frequency. So the output amplitude over the input amplitude, the amplitude ratio will be a function of frequency. And if we plot that versus frequency, we see that for a zero-order system, it's constant. There is no frequency dependence. It's just K. And the phase angle between the input and output sine waves is 0 degrees. There is no phase lag. If you input a sine wave at a frequency any frequency into a zero-order model, you get a sine wave out. Same frequency, no phase shift, and the amplitude is just K, which is the amplitude ratio of the output over the input. One might ask, what's the usefulness of a zero-order model? It's not practical, it's not realistic, nothing is zero order. And so I suggest to you the following. If you have a very high order model, but over some frequency range of interest, some frequency range of operation, for example, in this low frequency range below what we call omega cutoff, the system behaves like a zero order system. Amplitude ratio constant, independent of frequency, phase angle 0 degrees, independent of frequency. Then over this range of motion, a zero order model is most appropriate. It perfectly fits. To do anything more complicated, if all you're interested in is this range of operation, would be foolish. It'd be needless complexity. Here we see a RC electrical system and a spring damper mechanical system. They are analogous. Let's analyze both and see what that means. Here we have a resistor and a capacitor. Here we have a dashpot and a spring. The resistor is analogous to the dashpot. The capacitor is analogous to the spring. We assume here that there's nothing connected to the RC circuit, that I out is 0. Using Kirchhoff's voltage rule, sum of the voltage drops around the closed path equals 0. E in minus the voltage drop across the resistor, minus the voltage drop across the capacitor equals 0. E in minus the voltage drop across the resistor is IR. The voltage drop across the capacitor we define as E out. Next step, E in minus, in place of I, because the current I goes through the resistor, but then it goes through the capacitor. Using the constitutive equation for a capacitor, the current through the capacitor is equal to C times the time rate of change of the voltage across the capacitor. So for I put in C dE out dt times R minus E out. I rearrange, and I get this first order ordinary differential equation with constant coefficients. We identify this constant here, R times C, as tau, the time constant. And if I use my differential operator, I can then get my transfer function, E out over E in equals 1 over RCD plus 1. Let's go to the spring damper mechanical system. Here, I goes through the R and the C. They are in series. What's analogous to current? It's velocity. So the velocity of the dashpot and the spring have to be the same. And they're in series. Even though they look like they're in parallel, they're in series according to this analogy. So both ends of the end of the spring and the end of the dashpot have the same velocity, just as the resistor and capacitor have the same current. I is analogous to velocity. The input here is a voltage, the input here is a force. The output is the voltage across the capacitor. The output here is the force in the spring. So I write my force equation, force in minus the force in the damper minus the force in the spring equals 0. Force in minus the force in the damper is B times the velocity V. Force in the spring is minus Kx. But we want to include Kx as the force in the spring, so F in minus BV minus F out equals 0. F out is Kx, and if I take the derivative of that, I get Kx dot, or K times velocity. So velocity is F0 dot divided by K, which I substitute in here. So F in minus B times velocity, which is F out dot divided by K, minus F out equals 0. Rearrange terms. And I note that I have a first order ordinary differential equation with constant coefficients. Write it in terms of a transfer function with the differential operator d. The transfer function looks like this. The time constant is b over k. B is analogous to r, c is analogous to 1 over k. So I could have done the electrical analysis and simply written down the differential equation and transfer function by inspection after drawing the analogous mechanical system. Let's now look at two first order systems, a LR electrical system and the analogous mass damper mechanical system. Again, with the electrical system, we assume I out is 0. The system is not loaded by anything connected to it. L and R then are in series and they have the same current flowing through them. If I apply Kirchhoff's voltage rule, some of the voltages around the closed path is equal to 0. I have E in minus the voltage drop across the inductor minus the voltage drop across the resistor equals 0. Voltage drop across the inductor is L di dt. And the voltage drop across the resistor we define as E out. E in minus L, and in place of I use the current going through the resistor, which is E out over R. So I have minus L times the derivative of E out over R minus E out. This then reorganizing becomes this equation, which is my first order ordinary differential equation with constant coefficients. We define L over R as the time constant. Using the differential operator, I get my transfer function. The L and the R are in series. They have the same current. For the analogy, the damper and the mass must have the same velocity. One end of the damper is connected to ground. The other end of the damper is connected to the mass. They both move with the same velocity. I have an input force, and the output force is the force in the damper, just as the output voltage is the voltage across the resistor. Sum of the forces, force in minus the force in the damper minus the force of the mass equals 0. Force in minus the force of the damper is simply B times the relative velocity of the ends of the damper. One end of the damper is fixed, the other end of the damper moves with velocity V, minus B times V, minus the force, the inertial force, which is mass times acceleration, M times V dot. The output force is the force of the damper, and the force of the damper is B times V. If I take the derivative of that, I get B times acceleration, or V dot. And so F dot, the derivative of F out, which is the force in the damper, divided by B, is my V dot. Because F is equal to B times V, and F out dot is B times V dot. And BV is F out. So if I reorganize this equation, I get my ordinary differential equation with constant coefficients. M over B is tau. Could have predicted that because L is the same as M and R is the same as B. And voltage is the same as force. And so using the differential operator, my transfer function is given by that expression. So we see the analogy. Here are some first order mechanical systems with using pure and ideal elements. to create those systems, both translational and rotational. You can review these and see, make sure you understand why they are first order mechanical systems. There are two inputs that we use to analyze our mathematical model and our associated physical model. One is the step response. We input a step, usually a unit step at time t equals 0, and we look for the response of the system. So for a unit step, my differential equation for this first order system is tau in general form. It's tau E out dot plus E out equals K times E in. There are only two parameters in this first order dynamic system model: the time constant tau, the steady state gain K. I set tau to be 0.5 and K equal 2 for this simulation in Simulink, or rather in MATLAB, to show the step response. The transfer function is E out over E in equals K over tau S plus 1. S is the same as the differential operator. It's the Laplace variable. We use S in MATLAB. We use D at other times, but from a application point of view, they are equivalent. So I see the response in blue to a unit step at time t equals 0. And the output responds along this blue line. And I see that at tau seconds, in this case 0.5 seconds, the system is 63% of the way to the final value, which is 2. K is 2, E in is 1, steady state value is 2. And in 4 tau seconds, I can see that, and MATLAB helps me see that, the system is 98% of the way to the steady state value. So in essentially 4 time constants, the system, from engineering point of view, has reached steady state. So this is the first order dynamic system unit step response. And this picture should be something that you can reproduce on demand. You don't need the equation that describes the curve. We don't need to solve the differential equation. But for a step input, this is the response. This is the meaning of tau. In 4 time constants, we're at steady state. And that's what you need to know and be able to express again on demand. Let's look at the first order dynamic system frequency response. Now, frequency response means if we input a sine wave into the system and we wait till all the transients die away, the output will be a sine wave, same frequency. It has to be. The amplitude will be different, and there'll be a phase shift. Both the amplitude and the phase angle depend on the frequency of the sine wave that we use. So if I put in sine waves of different frequencies, and I plot amplitude ratio, output over input, in decibels, where a decibel is 20 times the log to the base 10 of the number I want to convert to dB, and phase angle in degrees, if I plot those points for varying frequencies, I get what we call the frequency response plots, or the Bode plots. We plot them on a semi-log axis, where the log scale is along the frequency horizontal axis. In the amplitude ratio, it's dB, so it's linear in dB. And in the angle, it's degrees, and it's linear in degrees. So I see here that if I were to plot for my first order system, the frequency response, in the beginning it's flat with an amplitude ratio of K, output over input. At a frequency of 1 over tau, the amplitude drops minus 3 dB, or 0.707 of the low frequency value. Now that happens to be the definition of bandwidth. The bandwidth of a system is the frequency at which the amplitude ratio drops minus 3 dB, or drops 3 dB, or is 0.707 of that low frequency value. For a first order system, the bandwidth is exactly equal to 1 over tau. And also at that bandwidth, at that frequency, 1 over tau, the phase angle is exactly minus 45 degrees. The phase angle starts at 0, at 1 over tau at the bandwidth, it's minus 45 degrees. It approaches minus 90 degrees at high frequency. The amplitude ratio, after it passes the bandwidth, will then take on a negative slope that's constant at minus 20 dB per decade, where a decade is a 10 to 1 frequency change. And you can see that right here. From here to here, it drops from 20 dB over this decade, from 10 to 100 radians per second. So this is the Bode plot, or the frequency response plots, for a first order dynamic system in terms of the parameters tau and k. Here we have two second order dynamic systems, an LRC electrical system and a mass spring damper mechanical system. Again, we assume no current is leaving this LRC system. I out is 0, there's no loading. So all elements have the same current flowing through them, they're in series. Kirchhoff's voltage rule says E in minus the voltage drop across the inductor, minus the voltage drop across the resistor, minus the voltage drop across the capacitor equals 0. E in minus the voltage drop across the inductor is L di dt, across the resistor it's Ri, and then across the capacitor we've named it E out. I substitute in for I through the capacitor is equal to C times the derivative of the voltage across the capacitor, which is E out, so it's dE out dt. So in place of I put C times dE out dt. In place of I, C dE out dt. And then if I simplify this, I get LC, the second derivative of E out with respect to time, plus RC times the first derivative of E out with respect to time, plus E out equals E in. If I write this in terms of the differential operator, I get this transfer function. If I equate it to a standard form, second order transfer function, which is Ks, divided by 1 over omega n squared times d squared, plus 2 zeta over omega n times d, plus 1. Omega n is the natural frequency of the system, zeta is the damping ratio, Ks is the steady state gain. By equating these two expressions, I find that omega n is given by this in terms of hardware parameters. Zeta is given by this in terms of hardware parameters. In this case, the steady state gain is 1. In the mechanical system, since I'm using the electrical mechanical analogy, I have a spring and a damper and a mass, and they almost have the same velocity, as all of these elements have the same current. So the spring and the damper, their ends are connected to ground, and the other end of the spring and damper have the same velocity as the mass. A force balance then tells me that F in minus the force of the spring minus the force of the damper minus the inertial force equals 0. F out is the force in the spring, like E out is the voltage across the capacitor. So F in minus K times X is the force in the spring, minus BV is the force in the damper, minus MV dot is the inertial force. Since F out is K times X, F out dot is K times V. V is then F out dot divided by K. So in place of v, I put this. In place of v dot, I put this, the second derivative of f out with respect to time, divided by k. I collect terms, or I simplify, and I get this ordinary differential equation of motion. It's analogous to my electrical equation. And I find my operational transfer function in terms of the differential operator, f out over f in, is given by this expression. If I equate it to the standard form transfer function, I get this with omega n equal to the square root of k over m, zeta, the damping ratio, equal to b over 2, the square root of 1 over k times m, and the steady state gain equal to 1. If you compare these two, having done one, I could write the other by inspection. I wouldn't need to do the analysis since they're analogous. For second order dynamic systems, the equation starts or a result of the analysis, it gives you a differential equation that looks like this. If I want to convert this to standard form, which is shown here, Q out is the output, Q in is the input, I could do it by just comparing these two equations, comparing the coefficients and determining what omega n, zeta, and k are in terms of A0, A1, A2, and B0. Well, I've done that for you here. So omega n equals the square root of A0 over A2. It's called the undamped natural frequency. Zeta is given by this expression. It's called the damping ratio. Ks is given by this expression. It's called the steady state gain. For the electrical system, here's the LRC circuit equation. For the mechanical system, the spring mass damper equation. And again, using these definitions here, I find that omega n is given by this expression, damping ratio by this expression, steady state gain by this, and then from the equation or from analogy, omega n zeta k sub s for the mechanical system. So here's a summary of my second order dynamic system model. Here's the ordinary differential equation, second order, linear, constant coefficient. Here it is in standard form with the values of omega n, zeta, and k sub s. Here's my operational transfer function in terms of the differential operator. Here's the step response of the second order system. And this is the unit step response. And the parameter that varies is zeta. So if zeta is 0, I get a sustained oscillation that neither decays nor grows. If zeta is 1, we call that critical damping. I get no overshoot, no oscillation, and the system takes quite a bit of time to get back to steady state. And so this is a plot of the step responses for a variety of values of zeta. Usually a value of zeta in the 0.6 to 0.7 range is most desirable, as it gives you the best trade-off between speed of response and relative stability, meaning rise time versus overshoot. Here's a picture of that step response. The rise time is the time it takes to go from 10% to 90% of the steady state value. M sub p is the overshoot, usually expressed as a percent. The settling time, the 1% settling time, is the time it takes to get and stay within 1% of the final value of the steady state value. And there's the settling time. Rise time and settling time, I have approximate expressions for this for a second order system. Rise time is approximately equal to 1.8 over omega n. The 1% settling time, T sub s, is approximately equal to 4.6 over zeta omega n. The overshoot MP is given by this expression, and it's exact. Zeta is between 0 and 1. And for zeta between 0 and 0.6, here's an approximate expression for the overshoot. Here's the frequency response of a second order dynamic system, again with the parameter being zeta. At low frequency, the amplitude ratio is 0 dB, or whatever the amplitude ratio happens to be. Here I show it as 0 dB. At high frequency, the slope is minus 40 dB per decade. And then depending on the value of zeta, I either get peaking behavior or I get simply a roll-off to this constant slope of minus 40 dB per decade. I note that the phase angle plots are different for each of the different values of zeta, but one thing is true. When omega equals omega n, all of the phase angle plots go right through minus 90 degrees. So the phase angle plots go from 0 through minus 90 at omega n, and then approach minus 180 as the frequency increases. This plot is very important for a second order system in order to understand the type of time response, the location of the what we call poles, or the roots of the characteristic equation of the second order dynamic system, where they lie in the complex plane, with the real axis being the horizontal, the imaginary axis the vertical. If one of the roots of that quadratic equation, that second order system characteristic equation, which is simply the denominator of the transfer function, if I have a root at the origin in the time domain, that represents a constant. A root to the left on the negative real axis represents an exponential decay. The farther to the left, the faster the decay. A root on the positive real axis represents exponential growth. The farther to the right, the faster the growth. If the roots are on the imaginary axis, then they correspond to a sinusoid that neither decays nor grows. And the farther you go up the imaginary axis, the higher the frequency. And lastly, we have roots in the left half plane and in the right half plane. If the roots are in the right half plane, what you get in response is a sinusoid that grows exponentially. So it's in a growing exponential envelope. And for roots in the left half plane, the roots are give a time response that is a decaying exponential. So it's a sine wave within a decaying exponential envelope. So these are time functions associated with points in the complex plane. They come from the characteristic equation of your transfer function. So now you can see when we talk about fast response, slow response, it all depends on where the roots of that characteristic equation, that denominator of that transfer function, where those roots lie in the complex plane. Like for first order systems, here are some pictures of second order mechanical systems with springs and dashpots and masses. And you can take a look at this and look at the translational version as well as the rotational version. This is a very important slide. Here is our second order dynamic system transfer function with the three parameters k, omega n, and zeta. The roots of this denominator are called the characteristic values. This is the characteristic equation if I set it equal to 0. And this tells me the roots of this equation and there are two, are located in the complex plane. They can either be real or imaginary or complex conjugates. If we assume they are complex conjugates, we have one above the real axis and one below the real axis, complex conjugates. And the roots can be located either by using a polar coordinate representation. Omega n is the radial distance to the root, and this angle theta has a sign that is equal to zeta. So the sine of theta is equal to zeta, the damping ratio. So using omega n and zeta, I can locate the roots, and the roots are symmetric about the real axis, so one above, one below. I can also locate them using rectangular coordinates because the roots of this equation can be written as minus sigma plus or minus I omega d. And the x coordinate is sigma, and the y coordinate is omega d. So you can locate the roots of this equation, s squared plus 2 zeta omega ns plus omega n squared equals 0, either using polar coordinates omega n and zeta, or rectangular coordinates omega d and sigma. And you can see how the roots are represented in either case. The step response of the second order system for an underdamped system has this as its equation. Now, no one expects you to remember that, but you need to remember what this response looks like. The rise time is the time it takes to go from 10% to 90% of the steady state value. There's an overshoot, m sub p. There's a peak time, pi over omega d. And there's a settling time, which is the time it takes to get and stay within 1% of the steady state value. And we've already said rise time and settling time have approximate expressions. The overshoot is exact and can be approximated when zeta is less than 0.6 by this expression. So this slide has a lot of very important information on it. So here is our second order system step response. I assume k is equal to 2, zeta is 0.3, omega n is 1. So I see here my response on the blue curve rises up, an overshoot, an oscillation, then it gets within 1% and stays there. And my rise time, my overshoot, my peak time, my settling time, we've all defined. And here I show the second order ordinary differential equation, and here is the transfer function associated with it. And here are the four expressions that we've talked about. Rise time, settling time being approximations, overshoot, peak time being exact representations or exact values. So this is what you need to remember in terms of an underdamped step response of a second order system, and what rise time, settling time, overshoot, and peak time mean in terms of performance indicators. Here's the second order dynamic system frequency response. I plotted it for two values, zeta equals 0.8, which is the red curve, zeta equals 0.3, which is the light blue curve. At low frequency, they are the same. And then the lightly damped system will actually peak and then roll off to a slope of minus 40 dB per decade. For zeta equal 0.8, it will almost look like a first order response, the way it just rolls off with no peaking. And however, the slope is minus 40 dB per decade. A couple of points to mention. When the frequency is omega n, all of the curves here in the phase plot go through minus 90 degrees. So to identify where minus 90 degrees is, or when the output lags the input by 90 degrees, look at the frequency is at omega n. And so you can see how the curves are different, but they all go through that point. The bandwidth for a first order system was 1 over tau. The bandwidth for this second order system is much more complicated. We tend to not use this formula. However, it does tell us what the bandwidth is, but you can see what the bandwidth is through this red line at minus 3 dB, where it intersects the curve. So there's one for zeta equals 0.8, but then at that intersection with the blue curve is where zeta is for zeta equals 0.3. And so then if the associated frequency with those points is your bandwidth. So this is the second order dynamic system frequency response. Input a sine wave, wait till all the transients die out. The output sine wave will be same frequency, but the amplitude will be different. There'll be a phase shift. Both the amplitude and the phase shift depend on the frequency. And that's what the Bode plots show. The Bode plots show an amplitude ratio, output over input, and a phase angle between the output and the input. This slide just summarizes what we've been saying. Here for the LCR system, here is your transfer function in terms of hardware parameters. Here's the transfer function in terms of performance indicators, omega n, zeta, k sub s. Here is the relationship between these two, omega n, zeta, k sub s, in terms of the hardware parameters. And the performance indicators in the time domain are rise time, settling time, and overshoot. In the frequency domain, bandwidth, the damped natural frequency, which is omega d, the peak amplitude ratio, the actual value of that peak value, and the frequency of the peak amplitude ratio, omega sub p. So you can see that omega sub p and omega n are not the same. And only when zeta is 0 are they the same. So, but it takes an awful lot of damping, high value of zeta, for omega p and omega n to be very different. In fact, we use omega n to represent the frequency of oscillation of the system, even though we know it's the damped natural frequency, which is shown here. Here the peak frequency for zeta equals 0 is the same as omega n, but for non-zero values of zeta, you can see the peak frequency and omega n are not the same. Here, the damped natural frequency is not the same as the undamped natural frequency omega n, obviously, and it takes a lot of damping to cause omega n to be significantly different from omega d, or omega d to be significantly different from omega n. So this summarizes all the important formulas that you'll need to use, and don't memorize, but you'll remember them by just repetition, using them to explain to others and to solve your own problems. Everything we've said up till now applies to a pure second order system, one that has a denominator polynomial that is second order and no numerator dynamics. What happens if we have numerator dynamics, if we have what we call a 0 in the transfer function? Well, this diagram I have here shows the x's as the roots of the denominator, the characteristic equation, where we take the denominator polynomial and set it equal to 0. Those roots, as we know, determine the transient response of the system, whether it's, in this case, it will be a decaying sinusoid, but how fast it decays and what its frequency is determined by position of these x's, these poles. The root of the numerator is -1 over z, and I indicate that as being a 0. So what happens to the response as z gets larger, which means that 1 over z gets smaller, which means the 0 moves to the right, gets closer and closer to the imaginary axis. Well, what happens is that if you ran these simulations is that as it moves closer to the imaginary axis, the overshoot gets bigger, so you can see that this is increasing z. The rise time goes down because the system gets faster, and the peak time goes down. You can see how the peak time moves, gets smaller and smaller, the peak time, and so forth. For the frequency response, what we find is that the bandwidth increases as expected, because if the system gets faster from a step response point of view, then it would get faster from a frequency response point of view, which means the bandwidth gets larger. So the point where it crosses -3 dB from the low frequency value is farther to the right, higher frequency. And as I increase Z, I also get higher peaking. So the resonant peak gets larger in the frequency response plots. And you can see it here also, the effect on phase. Well, now what happens if instead of having numerator dynamics, I have additional denominator dynamics? So I add what we call a pole to the denominator. And so as P increases, this pole, which we show with an X, moves to the right closer to the imaginary axis. What is the effect on the step response? Well, the effect on the step response is as P increases, as this gets closer and closer to closer, what happens is that the system gets slower, rise time gets larger, peak time gets larger, and overshoot gets less. So it overshoots less, the peak time is higher, and the rise time is higher. It's a slower responding system. What's the effect on the frequency response? Well, let's take a look at that. Here it is here. So the effect on the frequency response is that as P gets larger, the pole moves closer and closer to the imaginary axis. We saw the system get slower, so the bandwidth is going to go down. The resonant peak is going to get smaller because we saw that the overshoot went down in the step response plot. So this resonant peak is going to go down, and we see the effect on the phase angle. The advantage of knowing the effect of the zero and the pole on a pure second order system is that most often that's what happens. You have a pure second order system plus some additional numerator dynamics or denominator dynamics, specifically an additional zero and a pole. So we saw what the effect of a zero is on a pure second order system, both step and frequency response. And we saw what the effect of a pole is on a pure second order system, both step response and frequency response. These are good to remember, so when you're designing things or when you're just trying to predict how something's going to behave or change, if you add a zero or a pole, which is what we typically do when we implement control systems. Lead and lag controllers are simply the adding of poles and zeros to transfer functions. So when we talk about controls, this is very, very relevant. It allows us to predict very quickly with great insight what the effect will be. So that concludes the presentation on dynamic system response essentials. These are the most important concepts in the topic of dynamic system response, zero, first, and second order dynamic systems. This is information you need to embrace and make a part of you to explain, understand, get insight into what's happening in the systems you're working with and the problems you're solving. The rest of the notes on dynamic system response are for you to be used as a reference. Should you need more information about the mathematics behind this, it's all there for you. So thank you for your attention.